Hello, and welcome to another episode of Weave architecture. In the first section, I gave an overview of the Weave architecture in general. In the second section, I explained how a transaction flows through the system, through the decorator stack and the handlers, the different interfaces we use for messages and transactions. Now I will look more about how we actually implement a handler and a decorator, what the details of it look like. The first step is to look at the interfaces we use. The handler interface you see here takes a context, a KV store, and a transaction, and returns a result, an error. Check result and deliver to result are quite similar with slight differences. Both of them will map to an ABCI result type. Check has a slightly different field than deliver does. We've already talked deep about transactions. Let's look now at context and store, and then see how we pull these together. The KV store has a set of read-write access to a key value store as an iterator. So you can see it has a standard set, delete, get methods. All of them use bytes slice for key and values. They're backed by level DB and a Merkle tree, IOV tree on top of it. This implementation can be swapped out, but should be a Merkle implementation over a persistent storage layer. We also provide an iterator, which iterates from a range, start to end. And reverse iterator go from end to start. It returns an iterator object or an error. The iterator then has a next method, which returns them one after another. Next will return a special error done, if it hits the end of the line. Otherwise, it returns another error besides error done. It means actually we had an error reading. So you can use this as a very simple interface. We've simplified it from a 5-method interface before. And release can be called to, if you terminate early before hitting the end of the bytes, you can release it to remove all of the go routines and callbacks and all the other various links to the database you have kept open. When we have a KV store we talk about, we don't really just use a KV store, we usually use Cacheablek KV store, which allows us to make a temporary buffer. The main point here is when we error on a transaction, we don't want to implement partial states. And we don't want to maintain a whole bunch of text to see if it's going to work or not work. We can start it, and if we detect an error at any point, we can just abort and roll back to the last save point. This is basically just the idea of sub-transactions in a normal Postgres database or other SQL database, that you can make open a sub-transaction, and then you can commit that sub-transaction or roll it back to the save point. So when you make a Cacheablek KV store has a function cache wrap, which allows you to run a cache on it. And the cache wrap is basically a Cacheablek KV store, then a child store, which then can either write, which will push all of these cached updates back to the parent store, or discard, which means throw it away and do the cleanup. You don't technically need to discard it. It won't write anything, but this allows us to clean up memory, to avoid memory leaks. So a Cacheablek KV store basically is a parent which can have sub-transactions. A KV cache wrap is a sub-transaction. You can nest them indefinitely. And every time they can push back one level to the parent. Otherwise, they all implement the KV store interfaces. They all work like normal KV stores, except they allow levels of allowing sub-transaction and then allowing writing it back to the parent. Context is the other piece here. Context contains information in the current block, which you pass in from base app, as well as any other information the decorators want to pass into it. Most of that is authentication information, which we use for decorators. It's used based on Go context.Context as iterator array and very generic with some standard keys we use. We actually want to change that design. Issue 822 is trying to standardize those, so we just decide what keys we want to support, rather than supporting arbitrary interface map, which is very hard to serialize, for example, or to work with. So the information we have: block header, which is the block height, block time, the chain ID, the block signers, who signed that block, along with the commit info, which we can use to reward or punish validators for the uptime in protocol. We have a logger in. The logger is passed in because the logger may have information like the current transaction and context information in it. So we use structure logger, which takes multiple keys. So we want to not pass a logger in the constructor of the object, but pass it in each call, so that logger may be able to know the whole call stack. And authentication information, as mentioned above. The result returned basically is the ABCI Result object, which has data, log, tags, and GasUsed. Except the error, we pass return a result error. So the result object will always be success with error code of 0 and no code space. And if you want an error message, we return actually the error object, a normal error, go error, and then that will turn into a code space and error code on the ABCI Result object. In addition to that, we added a few more elements to the results we pass internally, which are used to signal stuff in our application. The first one is diff of validator update. It's a list of changes to the validator set. In the ABCI protocol, you must return a list of all changes at end block. However, we calculate the changes in each transaction. For example, if I have a transaction for a multi-sig contract to update the validator set in a POA system, or for my staking to update in a POS system, I will make that change inside one transaction. That transaction will notify us of the change to the validator power, and that changes will then be sent up the stack in the result to base app, and base app then can, as you saw earlier, can take that diff and then capture it to return it in end block. The other thing we pass through is required fee. This is a way of the handler passing information back up the stack. The required fee is used because we decided in our BNSD application for IOV, we realized that we don't have product fees. For example, we have an anti-spam fee for everything, but certain features like registering your name will cost a special product fee. This product fee is actually the usage of the blockchain. This is our product. So we can allow sending transactions or multi-sig usage at the normal anti-spam gas fee, but we can charge for a special custom product fee. This required fee is determined by the handler. So the handler can look at the message type, and it could also say, okay, depending on what namespace you're registering, will you charge a different fee. That information will be passed back up the stack and can be used in Decorators and their post-processing stage. The implementation of a handler is relatively straightforward. A deliver method will have to validate the message, which has its own validate field. It will, if it refers to an existing object, like execute an escrow, it will load that object from the KB store and check for consistency, and it'll check for authorization on it. If I want to release an escrow, I will say the escrow ID. Here it'll load the escrow ID, verify it's there, then it'll check who's the arbiter of the escrow, who's able to release it, which is stored in the database. Check that information against that was stored in the database against the information you have passing context of who actually signed it to see if it was allowed to be signed. Is our current context containing authorization to execute this? Then after it can error at this point if it's not validated. If it is validated, it will either create or update objects in the KB store, potentially move coins, which we call into Xcache, and then return the ID of any new object and result data. So if we create an object, we auto-generate IDs for a number of objects. We should return that in result data so it's easy to query for it. Result data is actually stored on-chain, so you can query it with TX search, and that will allow us, and also to return directly on the results. So you can get information back, and with the information you are able to find the ID of the object you created. If I say create escrow, it will create an escrow, and I don't know what ID it has. We assign the next ID. It's a sequence. So we return that result, so then I can query the escrow or use that or pass it to another function. Check TX is the same as deliver, especially it does the first 3 steps of validation checks. What it doesn't necessarily do is the actual execution, which is creating and updating objects, moving coins, and returning ID. We don't need to return the ID in check TX at all. It doesn't matter, but we can skip these steps or execute them. If we execute them, it takes a little more time, but it makes check.tx more accurate. That means if we execute check.tx in 3 independent ones, we have create escrow and then release escrow one after another, they'll actually both be valid, rather than the second one, the release escrow saying, hey, I don't know what escrow you're talking about, and it will reject it unless you wait a whole block before you submit those. This will allow you to submit 2 or 3 interdependent transactions in the same block if you implement the full checks in check. Yeah, it's a design decision, and I think there's a bunch of discussion also in Cosmos SDK about how much you perform in check TX, how accurate you want to be there, and how much you cut corners for speed. The decorator, as you mentioned before, and other things, basically works the same as a handler, except it has a next argument there. So it takes the same arguments, context, KV store, and checks, as well as a next step, which is another handler it calls into. The handler, it may be another decorator. We have a chain decorator function, which will take a bunch of decorators and each wrap them into basically with a next step along the line. So it turns the decorator into handler, because it just basically curries the next information into a little step, and then when you execute that step as a handler, and the step will then call a decorator with a next curried that next. So yeah, we just worry about making decorators with the next passed in, and then we have this little chain function which will handle that for us. That again was inspired by Negroni architecture. You should check it out. It's a very nice middleware package for Golang HTTP servers. This allows us to pre and post processing, as well as modifying the arguments, adding signers to the context or changing the KV store. So let's look at a few examples to understand the power of this, and go to implementation. So one first example is recovery. Recovery is a very simple example of a decorator. You saw it mentioned in our decorator stack, and what it does is check and deliver the same. It defers error recover. That's all it does. It's a decorator. It has this next thing, and then it will defer that and then call next check, pass them in untouched. It'll just return, call that one. This defer will prepare a panic handler before it calls that function. If this function returns an error, it will call that. So what error recovers does, if you're looking at this, is a standard one. Recover here then says it does recover, and if there is an error, it returns error panic. So it basically makes an error with information passed in. The next, another example is logging. That's a little more straightforward. Same thing, check and deliver the same. It measures the start time before starting the transaction. Then it calls the next step along the line. And if there is no error, it takes a log of log message. Otherwise, we have an error. And then we log the duration, so we know the time it ends at, right? So we basically say, okay, this is the context, here's a start time, here's a log message, and here's an error message we have, which may not be true, and then, yeah, whether it's deliver checked or not. Then they basically here just do a logging. Then at this point, we find the delta time, we add that duration to our structured logger, and then we log this information, depending whether it's an error message, debug message, info message, based on whether we have check or deliver. So this allows us to set some stuff up beforehand, start time before executing it, and then process the log message afterwards. So you see how the decorator design is very helpful here, because it allows us to execute stuff before and after the actual call. It's not doing them in order, it's actually nesting them, which allows us much more power inside the decorator. Save point is another more powerful one, which allows us to, well, on check and deliver, it will execute as needed. Checks is if it's, you can execute a save point on check or deliver, or both of them. So it may only, if it's executed, if it's not on thing, it just calls directly as a no-op. It just passes down the line without doing anything. If it is, it ensures that we have a Cachable KV store, as we talked about earlier. If so, it cache wraps it, checks if there's an error. If there's an error, it will discard the cache. Otherwise, it will try writing the cache. So you can see this method here is the same in deliver as check. It will basically do the, you see this cache wrap here? It will allow us to, this is one we can just put in the decorator stack, and it means any errors will revert all changes. Any successful things will commit the changes. Notice that we also handle the error that writing the cache out after executing successfully may cause an error. So if that errors, if we can't write to the database, we can't write the cache, then we also have to handle that error as well. So you see this could be added, and you don't have to worry now. We just put this in our stack, and at that point we say we put it in the stack where we want to, and everything executed before this save point will be written directly to the parent store. Everything written after this save point will be written conditionally to the parent store only upon success. If anything below it errors, then the whole thing, anything below it is not written. Another interesting one is key tagger. The key tagger, for example, makes a new recording store. It actually instruments, rather than instruments the KV store another way, it makes a recording store which will record all writes to it, actually. This one then it passes it in there. The recording store is passed in deliver. The deliver works exactly like a normal store, reading and writing, except it keeps a record of what it is. It can be cache wrapped to it. When this is done, if there is no error, it will then grab the pairs that are recorded and add those to the tags. That means these tags here are basically a list of the byte that was written, the keys are written. So we encode that key into a string, and then, well, we have S or D, whatever else. So we use, so we store the key that was written as a tag. That allows us to automatically, we can search for or subscribe to all changes to a given key automatically. We don't have to keep track of that in any handler. We just add this decorator there, and every time that you modify an account balance, it will automatically tag it with a key of that account. Once we've queried that account and know it wants what it is, we can then watch that account. So we subscribe to that, and every transaction that modifies it, whether it is me sending money to it, whether it is releasing money from escrow, whether it is a validated reward, whatever it is, whether it is a fee I spent to modify, I assign another transaction and change a fee, that will be there. I can subscribe to my account nonce as well, and every time that I assign a transaction, my nonce increments, and I will get a notification for it. You can do that for any sort of key. You can watch an escrow, you can watch the proposal to see when the proposal changes. You can search for it later and say this proposal changed at height 59, and search for the proposal. All changes the state of the proposal will then be searchable. It's very nice, and you don't have to forget about adding tags in some handler. We also have things like signatures also work. If you look at signatures, it makes sure it's a signed transaction. And well, we allow it non-signed. So remember how we said transactions can support other things? A signed transaction here is actually get signed bytes and get signatures. So if it's a signed transaction, if we use that for an application, the signature thing will say get the chain ID from the context, verify the signatures with this chain ID, and make sure the nonce is correct, which does all the hard work. If it's wrong, the signature failed. If there are no signers to it, then return no signatures. If this is successful, then we return, we update the context with the signers who signed it, and then pass that updated context into the deliver. So anything downstream of this decorator will have that full information. In this case, we only do a pre-processing step. We don't have a post-processing. So that is also a valid way of doing it. We modify the context, store extra information in, and pass that down. Right now, this is using custom keys. Again, we considered that in discussion of issue 822 to stop using custom keys, but instead use standard auth data. In any case, you can see the power here of decorators. They're very useful in many cases. And I hope they give you an idea of what you can use for, what you can use a decorator for. Both doing pre-processing steps as well as post-processing, like recovery, as well as both logging and the save point stuff, which does setup before it calls down to a function, and then based on the function it can react to it because it's done setup beforehand. Thank you for tuning in. We'll have another sections going on for more pieces of the Weave architecture. I hope you understand how handlers and decorators work here.